this one, it says to solve for x, and to undo the square root, we have to square each side. So I'm going to square each side of this equation. And when I do that, over here, the root and the exponent undo one another. So it gives me that. Over here, I've got the 121. And now from here, I just have to simplify this thing. So I'm going to add the 5 to each side. So I'm just solving for x. Let me bring that over here. That's a 2x equals 126. Divide each side by 2. So I find out that x equals a 63. And that's it. And I can easily go back and plug that in and check it. And I should, because remember, we can get extraneous solutions here. So plug it back in and you'll see that that one does indeed work. The next one, it says, when is the following statement true? When is k raised to the negative n power less than 0? And really, it has nothing to do with the n value itself. There's no n value that would make this thing negative, because that's what being less than 0 means. Really, the k value would have to be less than 0 to begin with. So k would have to be a negative. And really, if we get technical about this thing, the n value would have to be an odd number. Because if the n value is an even number, even if k is negative, once we raise it to that power, it's going to make it a positive anyway. So those are the two things that would have to happen in order to make this statement true. To get a negative, k would have to be negative to begin with, and I'd have to be raising it to an odd number to keep it negative. For this one, it just says, where is the following undefined? Remember, it's undefined when our denominator gives us a 0. So I'm just going to set the denominator equal to 0, or rather say that the denominator cannot equal 0. And now just solve this. And the first method I go to is factoring two numbers that multiply to a negative 14 but add to a 5. It's a 7 and a negative 2. So this one does factor to x plus 7 and x minus 2. And now I say each of those cannot equal 0. So really it's the same as solving, except we're saying cannot equal this thing. I subtract the 7 from each side. So here I get x cannot equal a negative 7. Here I add the 2 to each side, so I find out that x cannot equal a positive 2. Okay, so those are my two restrictions, my two excluded values. So this one, it says to find the quotient. Remember, to find the quotient, what we do is we change this to multiplying by the reciprocal. So I'm going to flip this guy and change this to a multiplication symbol. And I'm also going to factor everything. This first numerator I can factor. I build a bridge. That's just going to factor into an x minus 4 and an x minus 5. That first denominator is a difference of squares, factors into an x plus 5 and an x minus 5. And now again, I've changed this to multiplication. And really, if you want to think of this just real quickly, when I multiply by the reciprocal, it means I now have this x minus 5 over the x squared minus 16. And so that's what I'm factoring. The numerator can't be factored. The denominator is once again a difference of squares, x minus 4 and an x plus 4. And now I can reduce anything in a numerator with anything in a denominator. So the x minus 4s cancel out. I can cancel out a pair of these x minus 5s, maybe these two. And so when I look across the numerator, I'm left with an x minus 5. When I look across the denominator, I'm left with an x plus 5 and an x plus 4. Okay, and typically we'll just leave this in factored form unless the problem states otherwise. All right. For number 19, it asks us to find the difference. So now we're doing subtraction. And to do this, we have to get common denominators. Right. So the first thing we're going to do here is I'm going to factor everything completely. I can't see the common denominators if everything's in this simplified form. So I'm going to factor that 3x plus 9. I can factor a 3 out, which gives me an x plus 3. For this second one, I take that denominator, I build a bridge, and I come up with an x plus 3 and an x plus 1. So now I can kind of see these factors start to take shape. And really, I just have to make sure that each denominator gets the same thing. So the first denominator has a 3 and an x plus 3. But the thing he doesn't have is the x plus 1. Okay, so again, he wants the x plus 1, so I give him an x plus 1 over x plus 1. The second denominator now is a little bit jealous of this first one because he's got an x plus 1, an x plus 3, and a 3, and he doesn't have all that stuff. He's still missing a 3, so we're going to give him a 3 as well. So now when we look at the denominators, they each have the same 3 things, and that's what's important here. Okay, so my numerator here is an x plus 1. The denominator I'm just going to leave once again in factored form. So I just write all 3 of these factors. And now I can subtract these numerators, denominators stays the same. When I subtract, it gives me a negative 5x and a plus 1. And it's all over the 3x plus 3, x plus 1, and that's it. Okay, we subtract the numerators, denominators stays the same. On number 20, it asked me to graph the following. And I suppose I should have a graph on here. Let me go grab that. Okay, so now I've got my graph here, and really the best way to do this, since we haven't really talked about vertex form, is I would just do an XY chart. And remember, you have to keep this XY chart going until you find the vertex, okay? So you got to keep going until you find the vertex. So I'm going to start with 0, 1, 2, 3, 4, 5, maybe 6, and that should do it for us, okay? If I plug a 0 in, I get a negative 5 squared, which is 25 plus 3 is a 28. So right away, that is a huge value that I'm not even going to be able to fit on this graph. Okay, so I keep going. Maybe I plug the 1 in. That gives me a negative 4 squared is 16 plus 3 is a 19. So I'm getting a little bit closer. 2 minus 5 is a negative 3. I square it. That's a 9 plus 3 is a 12. So I'm getting a little bit closer. I plug the 3 in. I get a negative 2 squared, which is a 4, plus 3 is a 7. That's something I can finally actually graph here. If I plug the 4 in, that's a negative 1 squared, which is 1 plus 3 is a 4. If I plug a 5 in, that's 0 squared plus 3, which is 3. If I plug a 6 in, that gives me a 1 squared plus 3, which is 4. And so right there, now I can see my vertex. Okay, as soon as these values start to repeat again, I can see that they're symmetrical. And if I were to plug a 7 in, I'd get a 7 out. Okay, so I'm going to start to see these values repeat. So 5, 3. That's my vertex. Okay, I could also plot the point 6,4. I could plot the point 4,4. And really, remember, this is my axis of symmetry, which is why these values start to repeat. Okay, I can plot the ordered pair 3, 7, just up here somewhere. I can keep going, and I can tell that this thing is going to be a parabola. Okay, so set up an XY chart, plug in the values that you need to plug in until you find the vertex. You have to find the vertex. The other thing you could do is you could FOIL this out and then combine like terms and use the opposite of b over 2a to find your vertex. In this one it says, what's the value for c to make a perfect square trinomial? Remember, to do that, you take the b value, this guy right here in the center, you divide it by 2 and square it. So negative 14 divided by 2 and then square it. So that's a negative 7 squared, which is 49. Okay, so that's the c value that I'm looking for. For this one, it says, what is the domain of the graph shown? Remember, for this one, when you're doing domain is an x equals line, which is a vertical line. And if I take that vertical line and I drag it over my function, I just see where it touches. See, and because there's arrows on each end of this thing, that means this thing's going to keep going forever. So it's going to keep getting wider and wider and wider, which means I'm going to be touching here, 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 here. No matter where I put this vertical line, I'm touching the function, which means the domain is x such that x is all real numbers. And that's our symbol for all real numbers. Okay? That's it. For these, number 23, it says the graph of y equals 3x squared minus 6x minus 11 has a vertex at 3, 1. Well, we can easily check that. We do the opposite of b over 2a. So that's 6 over 2 times 3. And that gives me 6 over 6, which is 1. Well, that's the x value for my vertex. So right away, I know that this thing is false. And now I'm just going to plug it back in to get the y value. So I plug the 1 in. That's going to be 3 times 1 squared minus 6 times 1, minus 11, which is 3 minus 6 minus 11, which is a negative 3 minus 11, which is a negative 14. Okay? So I get 1, negative 14 for my vertex. And that's it. Okay? For number 24, it says the degree of the polynomial is 12. Remember, the degree of the polynomial is equal to the degree of the highest monomial term. And for each of those, we add the exponents. So the degree of this first one is a 15. The degree of this second one is a 3. The degree of this guy is 0 because there are no exponents. And the degree of this guy is 7, which means the degree of the polynomial is 15, which means this one is also false. Number 25, it says the y-intercept of y equals negative 3x squared plus 6 is 6. Well, the y-intercept is when we set this equal to 0. Or sorry, the y-intercept is when we plug a 0 in for x. So if I plug a 0 in for x, I see what I get. That does give me a 6, so that's absolutely true. Okay? For this one, it says the equation has one real solution, and the easiest way to check that, we're going to go ahead and add the 4 to each side, and we're just going to do our discriminant. Remember, if I have x squared minus 6x plus 4, I can use my discriminant, the b squared minus 4ac, to see how many solutions I have. Remember that if the discriminant is a positive number, it means there are 2 solutions. If the discriminant is negative, there's no solution. And if the discriminant is 0, then there's one real solution. So this one, I subtract the 16, and that gives me a 20. So I get a positive number for the discriminant, which means this is false. This one actually has 2 real solutions. Okay? And again, I'm changing the underlined piece of this thing. So there's 2 real solutions for this one. This one, it says this sequence is geometric. And if we look, geometric means I'm multiplying by the same thing each time. So that would be times 3. And when I multiply by 3 again, it does not give me the 30. So this one's clearly not geometric. It looks like the pattern here, I'm adding 12, adding 12, adding 12 each time. And so instead of being geometric, this one is actually arithmetic. Okay? And number 28, it says the product of y plus 2 and y plus 2 is a trinomial. And that's actually true. If I were to distribute this out, that's going to give me y squared plus 4y plus 4. So that is a trinomial. So that one's true. Number 29, it says the function y equals 3/5 1.3 raised to the x represents exponential decay. And really, this one is an exponential function, but this one's actually exponential growth because the b value is greater than 1. Okay, so the thing that's being raised to that exponent is greater than 1, which makes it exponential growth. Okay.